All right, so this is our second lecture in Chapter 8 that deals with internal flow. Everything in the last lecture was just a review of the hydrodynamics. We'll move into new material, thermal considerations. First of all, we have to talk about that thermal entrance length. So if you have a large tank and somehow you have a pipe here and you don't want to be a bunch of recirculation right at the edges of the pipe as the flow enters from the large tank, often you have a little bit of a bend or a bell mouth. Okay, don't worry too much about the bell mouth. What we're going to do is we're going to start measuring X from 0, and then it'll be down the length of the pipe. And there takes a certain region to become both hydrodynamically fully developed. We talked about that last time with the velocity profile. And now thermally fully developed. So I think it's easiest when you talk about developing a temperature profile to talk about a hot wall. What does TS represent? The surface temperature of the wall. It could be constant. That's easy for students to conceptually think about. And the fluid out here may be all T infinity, a lower temperature, color-coded blue. And if you look at this entrance region, just like the velocity, it was a uniform velocity, but here we're going to sketch temperature. So this temperature, T, everywhere at x equal to 0 coming in is uniform temperature. It feels, or the effect of that hot wall. So as you go down the tube, profile the temperature will first of all be severe at the edges, kind of flat across, until it gets to and beyond a region that you call X, fully developed thermally. Beyond that length, then it's fully developed. Well, what does it look like at that length? Draw it here, and we'll sketch the walls a little further, and we'll put T sub S and T sub S, and it could be shaped like this if it's laminar flow. Won't be a perfect parabolic, but it'll be close. What happens if it's turbulent flow down that length of that pipe? Well, then it'll be steeper gradients at the edges, and it'll be a flatter temperature profile in the core region, just like the velocity gradients were steeper at the wall and flat in the middle. We're trying to sketch temperature here. So after this region, or length, the temperature is only a function of R. And before it, the temperature is a function of R as well as distance. It's developing. So what are our equations? Well, if the Reynolds number, based on the diameter, is less than 2300, we expect the flow to be laminar. So fully developed laminar flow. And so the X fully developed hydrodynamically, can you remember that equation? 120 diameter Reynolds number. Well, guess what? The fully developed thermally is the fully developed length hydrodynamic multiplied by PR. I forgot. What is PR? PR. Prandtl number. It's a Prandtl number. And so you just multiply the hydrodynamic length by additional parameter PR. What happens if the Reynolds number based on diameter is greater than 2300? Turbulent, then the fully developed thermally will be about the same as the entrance region to be fully developed hydrodynamically. Because the mechanism that controls that temperature profile of these little mixing components of that turbulence been exposed to the entrance region. What I'm going to do now is I'm going to say we're going to talk about pipes that have itty-bitty entrance regions. We're now just going to talk about when it's fully developed. A lot easier, because when you focus, and once we have mastered when it's fully developed, what's happening, then we could possibly go back, if time permits, and talk about the mixing of the entrance plus then developed flow. All right. We have to go back and review Thermo 1. So we have a pipe, and we have flow flowing through the pipe, and we introduce a little CV. CV stands for control volume. What can cut across this boundary if there's flow coming down the pipe, what's going to cut across that boundary of the control volume? It'll be the mass. So there'll be some mass flow rate coming into the control volume, and the mass flow rate coming out of the control volume. If it's steady state, what do we know about the mass flow rate in compared to the mass flow rate exiting? They're the same, so we drop the subscripts. We just talk about m dot. All right. Now we can also have something coming across the wall of the pipe and into the fluid. And they use in Thermo 1 this big symbol. What is that? Rate of heat transfer. Would be the typical SI units. Kilowatts. Yeah, kilowatts. And then they also have maybe something with the shaft, and we'll do it like this. W dot out of the control volume. What would that be? Some power, some energy transfer that's organized in the form of work. So if you think about that and you say, okay, steady state, so no accumulation or depletion, but what the rate at which energy is flowing in by the form of heat transfer minus the rate at which it's flowing out in the form of organized energy transfer called a mechanical work out of that control volume. And then we're going to have, it comes in with that enthalpy. We're going to call this all inlet state 1, or I if you like that, outlet state 2, or E if you like that. And then it goes out with enthalpy 2. It could come in with the kinetic energy, go out with the kinetic energy, come in with the potential energy, minus out with the potential energy. So we could have changes kinetic, changes of potential, and oh, by the way, I forgot, what is this H called in Thermo 1? Enthalpy. What do we call H in heat transfer? Convection coefficient. Welcome to the confusing world of recycled notation and symbols. So look, we're not going to be interested in this class in changes in kinetic energy. We're not even interested in changes of potential energy. But we definitely are interested in changes in the enthalpy. We're not interested in this class in the change or power out of some organized, but we are interested in the rate of heat transfer into the control volume. So you look at this equation and you rewrite it, and I'm going to switch from Thermo 1 to heat transfer notation. Okay, that's why the lowercase q, I made a big deal of this early on in the semester. Lowercase q in this textbook is equivalent to cap q dot in Thermo 1. They have the same units, it's the same discussion. Is equal to the mass flow rate times H exit minus H inlet. This is a Q into the fluid from the walls of the pipe. It results in an increase in enthalpy. Now, a lot of times we're working with liquids. Liquids are incompressible. Even if we're working with gases and we don't have a huge pressure change, it's just flow at pressure, it's little pressure drop as you're going down the length of that pipe. The change in enthalpy can be related to a change in the temperature. The change in the enthalpy can be related to, so I can replace this by, maybe put down here, m dot times something. Don't call it out. Do not call it out. Some of you know this. T2 minus T1. Help me a little bit. Cap T, temperature. 2 is the exit. T1 is the inlet. I'm going to pause. I'm going to demic. I'm going to walk around. And you're going to fill in that blank in this equation. I'm starting off with the easy question because I just blew them away at 8:30 this morning. So what do we put right there? We put a C sub P. If you left off the P, great. That's okay. It's specific heat. But if you really want to be accurate, they would put a C sub P there, blah, blah, blah. All right. So that's a specific heat. So when you dump heat into the fluid that's flowing down, what you're doing is you're changing the temperature of the fluid. That brings us to a very complicated discussion. The mean temperature. Because we just had a profile like this and we said, oh, if the wall is hot and the fluid is maybe you get a profile of temperature in that flowing fluid such that if it's turbulent especially, it's going to be well mixed in the turbulent, and so the core will be essentially pretty uniform profile, temperature is pretty constant, but then it's going to be higher if the wall is hot as you move toward the wall, right? But you're saying that fluid near the wall isn't going very fast, because I remember our velocity profile, and if it's turbulent flow, it'd be like a plug flow, right? It would have a severe gradient at the wall if it's turbulent. If it's laminar, I've sketched this for turbulent. If it's laminar, then it's smoother. It's more parabolic in the velocity and parabolic-like in the temperature. All right. Well, somebody says, what is that temperature at that point? Well, I'd say, well, it's about this value. It's kind of the average. Or maybe it's closer to this value, right? Where I'm thinking of one temperature representing that flow temperature, that mean temperature. So how do we come up with this Tm, this mean temperature? We go back and we say, well, we had that mass flow rate times the specific heat times that temperature. I would like that to be the mean temperature. But what I think about is just instead of having one average mean temperature, if I did think about looking here at the round pipe, looking at the end of it, in the middle is where R is equal to 0, and then we have R going out from 0 out the cap R. And we think that for each little ring in here, just like we did for the velocity is constant in that little ring, and the temperature is constant in that little ring. And so we would say, well, I need to sum it up for each little ring. I need to do an integration. So we would do the sum, the integration, or over all the little ring areas of, I want to get that little bit of mass flow rate in it. That would be rho times the U times the dA gives me the little mass flow rate times the specific heat times the temperature. I have to emphasize, is this T a function of radius? Yeah. Is this U a function of radius? Yes, it is. I tried to sketch both of them up there to emphasize that. So here is my equation for T mean. It's 1 over the mass flow rate times the specific heat, the integral of density, U is a function of R, C, T is a function of R, dA. Somebody says, can we cancel those specific heats? Sure, you can. Somebody says, you know what? That mass flow rate, wasn't that rho U mean area? Was that true? Yeah, so let's substitute that in here. You can write this equation a few different ways. So you could replace that m dot by rho U mean area integral rho U T dA. Hey, do you think the constant density could be canceled? Sure. Sure. And so probably you could stop there, or you could even do this. What is the total area of the pipe? Pi cap R squared, true? And so you could put 1 over U mean pi cap R squared, the integral of U is a function of R, T is a function of R, and then dA, this little dA up here is 2 pi R dr from calculus. You could put the 2 pi R dr, integrate from 0 to cap R. Could we cancel the pi? You can change this equation around so much that it becomes very confusing. But think about it. What does this equation represent? It's a way to calculate the mean temperature. How do you describe how to calculate that mean temperature? Right here, maybe that's the easiest way to look at. Some students, if they've never seen how to this, they'll do this. They'll say, oh, I think the mean temperature is 1 over area, the integral of T dA. Is that the right answer for the mean temperature? What did it leave out? The velocity. And we're interested in the flow rate. And in the core, it has a faster or larger velocity, hence it has a larger flow rate. So it's not just this would be only an area average. Oh, it would give you a decent number, but it wouldn't be correct to 3 or 4 significant digits. It would have some error in it. It's just the mean temperature is just simply not an area average. But as soon as I multiply area by this mean velocity, what is that? It's not an area, it's an area times velocity, which is a volumetric flow rate. And then somebody says, well, hold it, didn't you have rho in there for one time? Yeah, well, what is rho times U mean times area? A mass flow rate. Volume flow rate, mass flow rate. Both of those have something in it. What's the key idea between the volume flow rate and the mass flow rate? It's the flow rate. It's the flow rate. And if you put in a C, I know that's a little harder to understand, but it's getting closer to a flow rate of the specific energy. But the key idea is the mean temperature is a flow rate average. All right, let's jump to a question. The mean temperature for pipe flow is an area average temperature, a volume average temperature, a flow rate average temperature, a radius average temperature. This is where the 830 class started to go downhill, because I didn't get 100% correct. And I thought I did a good job of explaining it. All right, we got to stop it. And why are we not all piled up on C? Why are we not all piled up on the correct answer? I don't know how to say it. I could say it's a volume flow rate, it's a mass flow rate, it's kind of like a specific energy flow rate. It's a flow rate averaged term. Okay, me bad. I can't explain things, but we'll press on. We have fully developed turbulent flow in a pipe. It's different than fully developed laminar flow. That was more parabolic. Turbulent flow is more plug or slug shape in the profile of both velocity and in the temperature. Here I've sketched it for the fluid being heated. If the fluid's being heated, what's higher temperature? At the wall or in the middle? Wall. Good. The temperature profile, T as a function of R, should look more like either A, B, or C. Please give me your answer to this second question. All right, we're going to close it down. The correct answer is B. What does A look like? Looks like hot fluid with cold wall. And what does C look like? But I kind of tried to show that this is 0 where this is not 0 at case A. And at case C it's 0. So maybe you might want to interpret that as the velocity, what it looks like, a velocity profile versus temperature profile. Where this one, because I didn't bring it to 0 at the wall, it looks more like a temperature for a case of laminar flow and the wall is cold. All right, well, we're done with that. Let's press forward. Oh, the punishment never ends. For fully developed turbulent flow in a pipe, that's going to be the focus of the study for a little while now. The convection coefficient, lowercase h, not to be confused with the enthalpy, is either a constant or it increases with increasing distance down the pipe. So if I wanted to plot it, I have h here, and here's x. It's all fully developed. And case A would be h is a constant. It doesn't change as I go further down the pipe. Or case B, it's increasing as I go down the pipe. Or case C, it decreases as I go down the pipe. Which is correct? Okay, I'm going to go ahead and stop it. And before we grade that one, what we want to do is ask a similar question about okay, what's this? Tau W. The wall shear stress. All right, for fully developed flow, that's turbulent, fully developed turbulent flow down a pipe, is the wall shear stress as a distance down the pipe, is it the same, constant? Does the wall shear stress go up with increasing distance down the pipe? Or does the wall shear stress go down with increasing distance down the pipe? That's our next new question. This is one, so go ahead and answer that one now. I'm going to have to stop, okay? Let's do this. If I have a pipe, and this pipe it has a distance x down the pipe, and all in here is the entrance region. It's minuscule. We're now beyond the entrance region. It's fully developed. And I come out here, and that's the entrance region, minuscule. And I have 1 inch or 1 foot or 1 meter of the pipe, right? Some length of the pipe. And then I have another inch or a foot or a meter of the pipe, and another inch or foot or meter of the pipe. And I think about, what is my pressure drop in this section of the pipe? Maybe it's, I don't know, so many psi. I don't know. And then I look and say, what's the pressure drop in this section of the pipe? 1 inch or 1 meter or 1 foot, whatever you're thinking, a common length, same length. You'd say, does it go up? Does my pressure drop go up? Or the pressure drop per unit length go down, or the pressure or go constant, or does it go down? See, I'm asking now about pressure loss, pressure drop due to viscous effects as I'm flowing down this fully developed turbulent flow pipe. So try that one. This is answer A, B, or C. All right. I'll go ahead and stop if everybody gets any last minute changes in. The majority of you are correct. It's just that I want more than just, I want a super majority. That's what I want. I want like a super majority. All right. Oh boy. Is this pressure drop per unit length, is that pressure drop per unit length proportional to the wall shear stress? Yes or no? Out loud. Yeah, we showed that before. So if you're consistent with yourself, if you picked A in the first one, you should have picked A in the other. Let me do this. One more question. Friction factor. The friction factor. Moody diagram, friction factor, right? We spend a lot of time on that. As a function of length down the pipe, it's fully developed. Does the friction factor not change? Is it constant, or does it go up, or does it go down as I go down the length of the pipe? A, B, or C? What is the friction factor doing? Same pipe. Good question. Yeah. Don't change the wall roughness. I didn't mention don't change the diameter either, did I? And I said ignore, I should have said things like that. Ignore temperature-dependent fluid properties, constant fluid properties, constant diameter, constant wall roughness. All right. Okay, I'm going to stop. So we're going to go ahead and now grade all 4 of these the best I can. So this is it. The friction factor is going to be constant. It's fully developed. You're not changing the diameter. You're not changing the viscosity, density of the fluid. You're not changing wall roughness. It's just a constant. And guess what? The pressure loss per unit length, dP over L, or per inch, or per centimeter, or per foot, that's going to be constant, right? So yes, a majority got it. Well, hold it. Is that 40 what? No, that's 62% got it. Okay, well, the wall shear stress is constant, fully developed. All related to the pressure loss, to the friction factor. And the very hard one, which still 50% had it from the beginning, but again, I was looking to get a supermajority, is that the convection coefficient is a constant and it's fully developed. All right. Okay, now that we know that it's a constant, let's press forward. Now we want to talk about, again, fully developed flow in a pipe with constant wall heat flux. What does a constant wall heat flux mean? So I have my pipe, bad looking, look there, try this. All right, and I maybe wrap electric wire around it, and I turn on the electricity to flow through that electric wire, and it resistive heating creates a uniform heat flux. And I wrap all of this in some insulation such that all of that heat that from that uniformly wrapped electric wire goes through the wall of that tube into the fluid. And so from the perspective of the fluid, you have Q double prime is a constant. You're just, for every little inch of pipe, you're dumping in the same flux. It's not increasing flux as I go down. This is the case of a constant wall heat flux. Hopefully you have a physical idea how you could experimentally set that up in a lab. All right, so now if I'm doing that, I really want to talk about the Tm as a function of x. Oh, here's the developing region. Forget it. I want to talk just only about fully developed region. What again is T subscript m? Mean temperature. All right. So does the mean temperature go flat? Does it increase with distance down the pipe? Decrease with distance down the pipe? Answer A, B, or C. And this is to help rebuild your confidence if you didn't get the other ones correct. All right, let's go ahead and stop it. And we'll take a look. And what's the right answer? B. Why is 64% said A? The last 4 questions all had answers A. You're seeing the pattern. Okay, well, sorry about that. I should have made that top one A. Then we'd had more correct. Why is it linearly increasing as we go down? Why is that mean temperature of the fluid increasing as we go down? Because you just keep pumping more energy in the energy balance. Maybe you take a little section dx from x to x plus delta x, okay? So there's the delta x thickness of that section. So if I said that Q double prime times the perimeter times dx, that's a little dA. This is a little dA. That gives me the little bit of Q that comes into the fluid from the walls. And that's going to result in not a change in the mass flow rate, not a change in the specific heat, but in a change of the mean temperature. The mean temperature at x plus delta x, won't that be greater than the temperature at x? I'm running out of room, sorry about that. So what we can do is you take this, and this is at x, and you divide this equation by dx, move that over here, and we have that Q double prime, which is a constant for this problem, times the perimeter is equal to the mass flow rate, specific heat, both of those are constant, times the rate of change of that mean temperature with respect to x. So dt m dx is equal to Q double prime P divided by M dot C sub P. Everything over there is a constant. The mean temperature is just a straight line. Increasing, increasing, increasing. Now, we already said that H for this problem is a constant. The convection coefficient is a constant. It's not changing as a function of x. This is the harder question. What does the surface temperature of the wall temperature, the surface temperature, do as a function of x? is the wall temperature as a function of x. Maybe I plot it on a different plot. T wall, not mean temperature. Is it constant? Does it go up or does it go down? A, B, or C with distance? What does the wall temperature do? All right, we stop. Okay, some people are correct, that's for sure. But we use this equation that Q double prime is equal to H T of the wall minus T mean at that location. Or sometimes I should have written this as S, TS equal to, or put an S here instead of a W. It's the surface or wall temperature. TS I think is more common in the book. Okay, so if this is constant and this is constant, is the temperature difference constant? Yeah, it's not changing. And so if the mean temperature is going up with increasing distance down the pipe, why? Because you're pumping more energy, heat into it. What does the wall temperature have to do? Go down? What? Somebody said go down? All right, if 6 people are just playing with me, don't do that, please. I mean, try to, if you're really lost, that's okay. But if you're just playing with me, I don't know what's going on. Hold it, what did I just grade? Did I grade it correctly? I got to go back. Darn it. How come you all are looking for A as the right answer? You fooled me. I shouldn't have said darn it, sorry. How come I only got 25% correct? All right, let's move on. Now you come to a harder one, which is we want to do this for a constant wall surface temperature. So let's do this one to rebuild your confidence. If I am doing the pipe going like this down the pipe right here, and this is X going down, I'm going to plot temperature. I'm going to plot TS. What does TS represent? The surface temperature of our pipe. All right, and for this problem, should the surface temperature of the pipe look like this? Answer A, or B, or C, and I'm only going to give 20 seconds. So this is the key word. It's constant wall or constant surface temperature. If it's constant, that means it's not changing with location. And so the answer, thankfully, we have a supermajority that's correct. But I guess 7 people are just playing with me today. No problem. Okay, now let's do this. I want to talk about the temperature of the fluid, the mean temperature, the single mixed or bulk temperature is what they call it, a mixing cup temperature. It's that mean temperature. It's a flow rate average temperature. All right. As it goes down the pipe right here, let's say it comes in at this value, and the TS, it's a hot wall, so TS is greater than TM coming in. It's a hot wall. All right. Does the mean temperature look like this, A, not change, constant? Or does it look like this, B? Or on this same plot, I'm going to put right here TS, because it's higher temperature than TM in. Right there's TM in, here's TS. Does it look more like this shape? Or does it look like that? So this is C or D. Go ahead. Tell me, what does that mean temperature profile look like? Let's go ahead and stop. And so we'll go ahead and grade. And congratulations. And now this is a more complicated profile. It's an exponential profile. How can the math show us that exponential profile? Well, this is the more complicated part. What you do is you come in and you say, for a little section from x to x plus delta x. We're going to think about the Q coming in from the wall into our fluid and what it does. So we have an energy balance that says coming in from the wall, Q in from the wall, this is double prime, put perimeter, put dx, okay, is equal to mass flow rate, specific heat, T mean temperature at x plus delta x minus T mean at x. Okay, we've done this before. For this, what equation do we use? We use the convection rate equation, which says that's equal to H times Ts minus Tm. True? That look good? Now, we can work with Tm. A lot of times it's better to just put in theta. What's theta? Ts minus Tm. Why do you want to put in theta? Well, because theta is a little easier to work with. All right, so here what we do is we have, I should have divided this by delta x, put that dx over there. So this energy equation is Q double prime perimeter equal to m dot c dtm dx. True? Okay. Now take and get the derivative of theta with respect to x. What is the derivative of, let me do this one, minus dtm dx. All right. One of these is 0. Either A is 0 or B is 0. Either the rate of change of the surface temperature, Ts, is 0, that's answer A, or the rate of change of the mean fluid temperature with respect to distance x is 0, answer B. Which one is 0? All right. Oh, come on now. Are you joking me? We got 3 people that can't answer that question? We are like 4 people. Oh, I had 3 for a minute. Somebody proved it. And they went, there you go. Up to 4, buddy. This is 0. That's the 0, isn't it? The rate of change of something constant with respect to distance. All right. So the reason I point that out is sometimes we lose sight why that negative sign shows up. And that's why it shows up, because of the definition of theta. It's a constant temperature minus that mean fluid temperature, which is changing. So that when you bring it down here, what you have is you have dTm, take this equation all the way down, dTm dx is equal to minus, hey, where'd that minus sign come up? I just showed you. All right, H divided by m dot, I left the, I got to put the H, P, m dot C, and then this is the theta there. Sorry. Couple steps I'm doing all at once. But I look at this. This is a first order ordinary differential equation. I need an initial condition. Theta at x equal to 0 is equal to theta initial. I now can solve it. I'll get the exponential solution for it. True? So the solution is theta at any x is equal to initial e to the minus hp divided by m dot c x. Do you like it or not? Does that equation look good? Thumbs up. All right, we got to press forward. I'm going to need that equation on the next slide or subsequently, okay? All right. Because this brings us to the log mean temperature difference. When you have a relatively long pipe, all right, or a longer section, and you have some temperature coming in here, and you can calculate the mean temperature of the fluid coming in, and you have some temperature here, let's say temperature of the surface at 1. And over here you have the temperature of the surface at 2, and you have the Tm out at 2. What you could talk about is you could talk about the delta T on one end Ts1 minus Tm1. And you could talk about the delta T at the other end, Ts2 minus Tm2. Okay. And you can have 4 different temperatures, but you'll have 2 temperature differences, one at one end, one at the other end. And what you're interested in is a very simple rate equation for this whole system. The rate equation would be something like Q is equal to some H, some constant uniform H over the whole system, some overall area. Hey, you know that overall area is the perimeter times the length, times some the different ways of writing it. Delta TLM, I think that's the way the book writes it. You have this LM subscript on delta T. It's the log mean temperature difference. What is the log mean temperature difference? Before we derive it, let's just show it. Log mean temperature difference is the delta T on one end minus the delta T on the other end divided by the ratio, the natural log of the ratio, delta T1n divided by delta T2n. That's the log mean temperature difference. All right. How in the world do we derive that log mean temperature difference? Well, you go back and you want to make sure and see why you need it. If I plotted temperature as a function of x going from 0 entrance to L exit, and I had my surface temperature high, and let's say that's uniform. It doesn't have to be, but it's easiest to think about it being high and uniform. And we come in this side with cold fluid. The outgoing fluid could do something like this. There's a whole spectrum of ranges of behavior. It could be just heated a little bit and go out just increased a little bit. Or it could go out where it's been increased and it's just been sitting there and it's really not been picking up much anymore. A whole range in between. It could be like this. It could be like that. It could be like that. See? What is that mean temperature doing? And this equation works for all cases. All of those cases. All right. So how do we get that temperature? Well, go back to our equation. What was it that we had? Let's do this. It'll take me a little bit to derive it, but Q overall is the mass flow rate specific heat Tm exit or 2 minus Tm inlet 1. Does that equation make sense? Does it make sense? From our overall energy balance, it makes sense. You can then take this and put the m dot C sub p, or leave off the p on it, and you'll have Ts minus Tm1 minus Ts minus Tm2. What did you just do there? You added and subtracted Ts and just rearranged it such that this is the mass flow rate, specific heat, constant pressure times our theta at 1 minus our theta at 2, our temperature differences. This is another way of writing theta 1, theta 2. All right. So now I need to scroll down a little bit. I'm going to need a little more room. But we have our solution to our temperature profile, which was that, theta at 2 at the exit is equal to theta at 1 e to the minus HPL. I put in x equal to L for the outlet, divided by m dot C. True? All right. Rearrange this. So we're going to have theta 2 divided by theta 1. Take the natural log of that, and you'll have minus HPL divided by m dot C. Did I lose you on that? 2 steps? All right. It's getting close. What we do up here is we look and we say, I want to reuse this equation to replace m dot C in this equation at the bottom. So we eliminate m dot C, and you'll pick up that this is equal to HPL divided by Q, theta 1 minus theta 2, equal to that negative sign. You'll have the natural log of theta 1 over theta 2. All right. So Q is equal to H PL theta 1 minus theta 2 divided by the natural log of theta 1 divided by theta 2, and QED. In Latin, as we wanted to show, we have now shown. It's been demonstrated. So that's the appropriate temperature difference. This is our log mean temperature difference right there. All right. Let's press forward. What time do I have? I've got about 3 minutes, don't I? Here it is in another shot. Basically, I had worked it out before I came here. All right. Let me stop here then, and I'll start the quiz.